Okay, thank you. Thank you for this warm welcome. So let me share my screen. Yeah, I would like to share the whole screen. Is my screen visible to everyone?
Yes, sir.
Okay, thank you. Thank you. So today I am initially will start our discussion with the introduction of with machine learning. That means
Sir,
to say we need to know
hello.
first of yeah, hello. Hello.
Sir, please make the full screen of the presentation. Yeah, now it is visible.
Is it
Right.
yeah, maybe there is some delay. It is
Uh,
taking 1 or 2 seconds.
it is full skin now, I think. It is full skin showing
Okay.
from my.
Okay. Thank you. So first of all, I would like to talk about what machine learning is, and later I am going to demonstrate that how it can be used for various type of application, like renewable application also we can be used. But first of all, let us delve into what machine learning is and what are the areas it can be used for. So before discussing this, uh, we all know that our human brain is capable of doing multiple things. So why? Because human brain has billions of neurons, and all the neurons work in parallel to give us the desired output, and that helps us to make the wise decision and all. So, but though the biological brain is not as fast as nowadays supercomputers, which work in nanosecond, but still our human brain are capable to work better because the number of brain neurons are too much in compared to the physical computer, and another thing is that they are highly parallel. So that is the main advantage of our biological brain, and that is why they are much better still now than the computers. So, but still, we can take advantage of this concept of our brain in artificial computer network or artificial neural network, which precisely say. So, in artificial neural network is a particular type of machine learning algorithm. So, I will not directly jump into the ANN. Rather, I will talk about the basic of what machine learning is, and after that, I will slowly move towards the direction of ANN. Okay, so suppose what concept the machine has. So machine basically erase our laborious task. Like suppose if I want to do a Xerox. So sorry, if I need to write a particular letter or something, and if I need to uh, provide it to 100 people. So earlier days, what even before the carbon paper, people used to write by hand all the 100 letters, but nowadays it is not required. All we need to do is to we can have a Xerox machine, or we can have a Xerox machine can do it 100 times without any human intervention. Means while writing it in a blank paper. So that is the advantage of a machine. Machine basically saves our time and help us from a repetitive task. But still, machine having some limitation. Why? Because machine cannot make their own decision. Like I can fix some device, like if the weather is sunny, I can plant the water the plants, or if weather is already rainy, in that case I don't need to plant the water. So I can fix certain rules and make sure that it will do our job. But again, it is predefined. So, based on the changing environment, we cannot make our decision. And that was the limitation of traditional machine. But human brain are very good at decision making. Human brain are very good at changing, adapting with the environment. So adaptability and the critical decision making are making human a human and machine a machine. So how we can integrate these two to get the best out of both the human as well as machine. So from there, the machine learning concept comes up, and so it is the algorithm that is soft, that means flexible and adaptive. So today, the temperature at which it is providing the water to the plant or generating some energy from the solar power. So next day, the input may be different, uh, still it may be providing us the output. So obviously there is no hard rule because changing on the environment, we need to adapt ourselves, and based on that condition of doing certain action also need to be changed, and that is the concept of machine learning. So suppose, let me explain with a very simple example. Suppose a person go to the vending machine every time and choose tea as a beverage. So after a certain period of time, machine should stop asking that person for tea or coffee, and it should wait for maybe 5 seconds. It will wait when a person will come in front of vending machine. There may be one camera, and it will detect the face of that human, and it will recognize that this human being always asks for suppose tea from that vending machine. So in that case, it will wait for a time like maybe 10 seconds. It will wait for his decision. But even after 10 seconds, if he do not provide any input, then automatically by default it is going to provide tea to that person because he prefer tea over coffee while getting for while asking for any beverage. So that is how we can use or exploit the experience seen by that machine, and we can leverage that to get our job done in a more adaptive manner. So just like a particular child. So how a child recognize whether a particular fruit is pineapple, orange, or apple? So obviously, initially, what the caretaker or caregiver what they do to the child, they basically show a particular fruit, and if that fruit is apple, they say, "See, this is an apple," and next day the same caregiver can show a different type of apple and again say that this is another type of apple, but this is also an apple. Similarly, the parent or caregiver can show pineapple and orange and explain that kid that this is a pineapple or this is orange, which is a different fruit. So this is how the caregiver or parent can teach a particular kid how to identify a particular fruit. So one day, when the parents are not suggesting the particular child what fruit it is, but by looking at the fruit, the child can itself, himself or herself identify which fruit it is. So this is how our human brain works, and the same technology can be incorporated into a machine. Now, before delving into the machine learning or using machine learning for our real life applications, we need to know certain concepts. Like, as we have learned in our previous example, a machine for efficiently adapting with the environment, it needs to have some experience. And experience can only come from some data set. That means the data set which has shown to the child or which has been seen by the vending machine. So only after have getting experience from a certain set of examples or samples, the model will get it knowledge and can work in unknown environment or unseen sample. So from there, the concept of features and labels come. So a machine learning algorithm is trained with a set of samples or examples called dataset that provide experience to the model. Like if I want to make a machine learning model properly identifying a dog from a cat by seeing an image. So what initially I need to do, I need to train that machine learning model with multiple dogs and cats images. And after, so as well as showing them the image, means I am showing the image of a dog, as well as I am telling the machine, see, this is a dog. Similarly, I am showing an image of a cat to the machine, and I am also telling that, see, this is the image of a cat. So this is how the image is the feature, and the label is the name associated with it. Like if I show an image of an apple to a particular child, the image is the feature. The number of pixels in the image existing, those are the features. Whereas the value or the name associated with, which is maybe apple, or in case of dog cat classification, maybe the image is of a dog. So this is the label associated with those features or pixels or input image. So this is the two important key of the classification or any other machine learning task. So basically, we from there the concept comes that labeled data, the data which has features as well as labels, they are called labeled data. So this is a set of data for which we already know the final output. Like an image, also I know the image is of a dog or a cat, or maybe the image is of a apple or orange. So we know what type of image it is. So this is the label data. So in our example, suppose I have two input like TLL and SD. Suppose I have two picture, as we can see in the below right side table, we have multiple inputs. So here in this example, these are the each row is showing one example or one sample. Whereas the left panel input, these are the features. So in our example, the TLL and SD, these two are input features, whereas the output may be the production yield or label associated with it. So features are the independent input variable that determine the value of the dependent output variable, also called label for classification problem. Here in this example, I can see that each row demonstrating a particular example or sample, whereas the TLN and SD, these two are independent input features, and their corresponding output or label is 40. So I hope the idea is clear what label data is. Now, if I remove the output from this data set, it will become unlabeled data, because the data in that case contain only the input features, but no class label will be there. So in that case, we can say it is unlabeled data. But in this example, this is labeled data. Now, I am going to introduce another very important concept, that is what is training data and what is test data. So suppose I need to teach a particular child what is apple and what is orange. So in that case, obviously I will show multiple images of apple and orange to that child, so that uh, the child develop the understanding how an apple looks or tastes, and how an orange looks and tastes. So that particular child will develop an experience that how a particular shape of apple looks like, and how the shape of an orange look like, shape, color, taste, etc. So this is the training. We are training the child or any model by showing the examples. Now, after a certain time, suppose the child is alone in the home, and suppose the child opens the door and he want to pick apple. So obviously the child should be able to correctly recognize what the apple is, how it is different from orange, and accordingly the child will pick the apple and eats it. So obviously that is called the tasting. Like now this is a new environment, a new apple fruit is shown to the child, and I am not supervising the child that see this is apple. I am asking what fruit it is, and the child should respond correctly. In that case, I can say that child has developed the understanding how an apple is different from orange. Similarly, in this example, we can see the last row, that is the taste sample, where the label is absent, and I am asking the machine learning model what the corresponding label or output should be. So what in this example, the first row 10 and 5, these two are input. If I feed into the model, the ML model should give us the output 40. Now, if it do not give the output 40, I will train the machine learning model in such a way that it understand that if the input is 10 and 5, output should be 40. Similarly, if the input is 16 and 20, the corresponding output should be 16. Similarly, in the third example, if the inputs are 35 and 27, the corresponding output should be 28. So while feeding those input, I am also telling the output to the model so that accordingly the model can correct itself, rectify itself, improve itself, so that next time if I again show the input 35 and 27, the model should give us the output 20. But while evaluating how good my machine learning model is, if I need to evaluate my model, I should not feed this data because machine has already seen 35, 25, corresponding output is 28. Machine has seen this example. So even if I feed 35 and 27 as input and machine give us 28, it may happen that machine has memorized. If these are the set of input, the corresponding output should be 28. So in this example, if I feed a training data to the model and if I get the output, I cannot be assured that model is correctly recognized it. So we need to evaluate how good a model is. To evaluate how good a model is, we need to test with a data which we have never fed it to the model. So if I feed the values 15 and 58 to the model, and if the model can correctly give us the output by understanding the relationship between the input features and the output, in that case, we can say that our machine learning model has generalized well and performing well. So this is the concept behind training data and the test data. In the meantime, I would like to ask, am I clearly audible? Hello, am I clearly audible?
Yeah,
Yes, sir,
clearly
you are
audible.
audible.
Okay, okay, thank you. Because I heard some noise, that is sorry. So this is the training data by which we are providing the experience to the ML model, and this is the test data by which we are evaluating how good our model is for real life scenarios. Now, what should be the training data and what should be the test data? Like, suppose let me provide a simpler example. Like in an exam hall, suppose I am a mathematics teacher. If I provide very simple example in the classroom, so students will learn the simple examples, simple concept. Now, if I give very tough example in the exam, which has never been taught, the related concept has never been taught in the class, the student will eventually fail or do not perform as expected. Why? Because the training example was quite simple, and that does not reflect the actual concept that student needs to know, that is going to be exposed during testing. So training again, if I teach very difficult problems in the class and give very simple example in the exam, every student will be able to answer all the questions. So again, we cannot judge how the model good is. So due to that reason, the model performance is highly dependent on the training data. So we cannot biasly choose the training data to train our model. So that is why most of the time in current days in real life data, all the time, the training data and test data are already predefined. So you can see a data set which contain two folder, one folder for the training data, another folder for the test data. So use the data within the training folder to train the model, and after that use the test folder data or any new data to test the model. This is how real life experimentations work. But suppose it is not there. Suppose there is no distinction between training data and test data, and we need to perform classification. In that case, there is a very wise technique used by the ML scientists, that is cross validation. So we can unbiasedly we can divide the dataset into multiple folds or blocks, and we train the ML model with a block and test the model with other block. So let me explain with this example. Suppose this is my data. So I can divide the data set into multiple blocks. In this precise example, I have divided my data set into 5 blocks. So I can use the 4 blocks to train the model and the 5th block to test the model. So suppose I have 100 training samples. Suppose I am having 100 samples. So I can divide it into a block of 20 samples each. And I can use 4 blocks, means 4 into 20. I can use 80 samples to train the model and rest of the sample to test the model. So obviously, I will get a score corresponding to it. Say the score is score 1. Similarly, in the next iteration, I am going to train the model with block 1, 2, 3, and 5. Whereas the fourth block, the next time, the fourth block is used for testing the model. So similar fashion, we are going to use one block for testing and rest of the block for training. And this is how we can evaluate the model for each block. And after that, we can take the average of it and we get to know how efficient the model is. So this is how, in an unbiased fashion, we can evaluate the performance of a model. Now, let me explain. Suppose I want to perform a prediction or forecasting in real life, like what should be the temperature of the next day or any other thing. Suppose I want to forecast a future value, like what should be the solar energy that will be generated, and accordingly, I may design solar panel or something. So, suppose I need to forecast something or predict something, I can use ML model. See how I can use it. So let us assume, suppose any production yield of a particular company is Y. Suppose the production yield of a particular company is Y. This is the output. And whereas the input may be two features, PLL and SD. And I can assume that Y, the output, may be a function of the X, where X are the set of features. In this example, PLL and SD are the two features. So I am going to train the model with different combinations of TLL, SD, and after that I am going to evaluate the performance of the model. So in general, we use 70% of the data to train the model and 30% data to test the model. But obviously, it depends on the scenario. Sometimes we need 70% training data, 20% validation data, and 10% test data. So it's all based on the situation. But this is a convention. If my data set is only need to divide it between training and test, this ratio can be used. Now, different problems can be solved by machine learning problems. Suppose I want to perform classification. Suppose I need to perform, like I told earlier, suppose I need to classify dogs from cats. So by seeing an image, I may need to recognize whether the particular animal is dog or cat. Or suppose I am driving an autonomous vehicle, and in front of the vehicle, some kid is running away, running. So obviously, if there is some camera, in front of my autonomous vehicle, so the camera should capture the child which is running in front of the vehicle, and accordingly it should press the brake so that it should not hit the particular child. So obviously, the camera will capture the image of the road in the front side, and if that particular image contain a child, then it should press the brake. But if the image do not contain any child or any living animal or obstacle, in that case, it should not press the brake. So this is how things work. So we can, in front of autonomous vehicle, we can put a camera. The camera will constantly keep on taking the images of the front of the vehicle, and if it find out any obstacle or child, then it will press the brake. So it is a kind of classification problem, whether any obstacle or living animal there in front of the vehicle, or if they are there, it will be maybe class 1, we should press the brake. If no obstacle or living animal is there in front of the vehicle, I will keep on driving. So I will not press the brake. So it is a class 0. So this is how the classification problem can be done by using machine learning algorithm, the first one. So obviously in that case, it is working on discrete values. So obviously the output will be either 1 or 0. If it is multiple class, then output can be 0, 1, 2. So output will never be a real value. Output will be a fixed value. Or suppose I'm passing a mail. So I can install a software that is going to detect whether my outbox mail, which I just received, is a spam or not. So based on the previous experience of the sender, content of the mail, the Outlook ML software is going to detect that mail is spam or not. So these are the very simple example of classification. Another problem that can be solved by machine learning, like clustering. I am going to discuss them in a more detail in next few slides. So clustering means grouping the same type of items. Like suppose there is a agricultural cornfield is there. So and in the cornfield, suppose the wheat is mixed with wheat. So I can use clustering algorithm, and clustering algorithm will group together the healthy crop from the unhealthy wheat crops. So this is how the clustering can be used, that will group together similar items and separate the dissimilar items. Third problem that can be solved by machine learning is regression. That means approximating the average temperature of the day. So if I can provide some temperature of a particular every day of a year, and I can ask what should be the temperature of that day of a year. So machine learning model by previous experience can state us what will be the average temperature of that day. Or if I want to predict the price of a home, so yeah, by checking the earlier price in that area based on the square feet, it can tell me what could be the probable square feet price of particular house in that area. So this is how a regression problem can be used to perform prediction or future forecasting. Now, I am going to talk about three types of learning. One is supervised learning. Supervised learning is a type of learning which can be used for both regression as well as classification. But supervised learning, the data contain input feature as well as class label or the output value. Like in the previous example, I have shown that input TLL and SD, those are the input features, and corresponding output value, production yield, I have also provided. So in this case, the data contain the input feature as well as label. And this type of, if I feed this data to the model and try to train the model, this type of training is called supervised learning. As you can see in this example, the input data is the raw data, and ML algorithm is there. I am feeding the data to the model. model is evaluating by seeing the raw input. Model is evaluating an output, predicting an output. After that, predicting the output with the original output or desired output. So obviously there may be some error because our predicted output may not be perfect as the original output. So based on the error, the supervisor is nothing else but the error. It is going to tell the ML model that this is the error generated by the model. So improve the model accordingly so that the next time the error will be less. So I will keep on feeding the data to the model, and model is going to evaluate how much error it is generating and expected that after each iteration, the error will be keep on reducing. So when the error will be close to zero or the error will get saturated, that means no further improvement in the error is possible. In that case, we will assume that our machine learning model completes its training on the training data. And after that, we will feed some test data to the model and generate output from the model. And in this test data, whatever the error is model is going to produce, that will be our real life error or test error. See this example. This example, we have used a convolution neural network. So we are feeding the image of dogs and cats. It is going through multiple layers, and after that, it is predicting the output that it is a cat. If I feed an image of a cat to the model. Similarly, after training, if I feed an image of a dog to the model, model should properly recognize the animal as dog. Obviously labeled photo, because I am not only providing the image, simultaneously I am also telling the model, see, this is the image of a cat, see, this is the image of a dog. An unsupervised model where no label is there. See this example. Suppose multiple colored coins are there. Suppose some blue coins, pink coins, yellow coins, green coins, all different coins are mixed up. And I want to separate them based on their similarity. So here, based on, as we can see in this GIF image, that based on the similarity, we are separating the coins in different groups or clusters. So obviously, based on the color feature, those are similar to green color, they are grouped together. All those are similar to red color, they are, or pink color, they are separated in a different position. And if they are totally different, so the distance between two cluster is based on the dissimilarity between two different samples. So if two samples are quite different, their cluster should be farther away. If the two samples very similar, they should be in the same cluster. So here no supervisor, no label is there. I have not telling that this coin belongs to red group, this coin belongs to green group. The model itself trying to analyze the features of the inputs and judging whether it is similar to the other sample or dissimilar to the other sample. Very well-known clustering algorithms are K-means algorithm, DB-scan algorithm, that they are used for clustering. So let me explain the one of the primary important thing, that is regression, because regression model is used for forecasting and prediction, which are majorly used for weather prediction or related technological development like sustainable technology development, renewable technology development. We need to know the future wind speed. We need to know the future solar irradiance. And how we can know that? By using the regression technique. So as we can see in this example, the left-hand side image, in the left-hand side image, we can see we have multiple input-output mapping. So here in this example, we can say that X are the input values and Y are the corresponding output values. So in this example, Xi, if the input value is Xi, the corresponding output value will be Y. Similarly, these are all data points where input is a one-dimensional value, a scalar value of x, and output is again one-dimensional value or a scalar value of corresponding y. And this is the function, that dotted red line. This is the function which is actually depicting the data set. That means the characteristic of the data set. This is the true hidden unknown function which is depicting the relationship between the independent variable x and the dependent variable y. Now, if I train a machine learning model will can learn in a two different ways. See, the left straight line and the right curve. So in the left straight line, it draws a straight line that tries to approximate what could be the relationship between the input variable x and the output variable y. So as you can see, the straight line is not a good predictor. Why? Let me explain with an example. Suppose this is my x value. So this is the x value. What should be the y value? According to my machine learning model, which is a straight line, according to that, this will be the corresponding y value. So this is the corresponding y value. But obviously it is not correct, because if I look into the original hidden function, this is the original hidden function. And accordingly, if this is the x value, the corresponding y value is this one. So this should be the y value, but our model is giving this as the y value. So how much error this model is generating? This much error is generating. So this ML model is not good enough to evaluate for the test performance. Now, this type of model is called underfitted model. Now, let me try to see the right-hand side picture. In a right-hand side picture, let me again some unknown input. Suppose this x is the unknown input. So according to the curve, that is my curve, which is depicting the relationship between input and output, according to that, this should be the corresponding y value. So this should be the corresponding y value. But in reality, this dotted red line, this was the actual curve. So if this is the x value, the corresponding y value should lie in here actually. This is the actual y value. So here the error of the model is this. So this model is again, as you can see in this example, this curve is trying to go through every training sample. So it tries to minimize the training error as much as possible. And if you see in this example, the training error is actually zero, because it is properly going through each of the training samples. But this model is overfitted model, as it is so blind to produce the zero training error. It is not clear. It is also adapting the noise in the real life scenario. Like we all know, the real life data are never perfect data. Any medical image data, real life forecasting data, the data always contain noise. That means some wrong value. So basically, suppose this input this should have been here, but due to some noise, this is in here. Similarly, for this input x, it should have been here, but due to noise, it is in here. So this kind of noise in real life data is always there. And if my model is trying to blindly get to the point of zero training error, obviously this model may not work in real life test scenario. So this kind of model is called overfitting model. So we need to do a trade-off, that model should not be underfitted or the model should not be overfitted. Rather than model should be somehow similar to this uh, test red curve, so that it can work on the actual test scenario. So there are various metrics are there to evaluate the performance of a model. One of them is mean squared error. Mean squared error is what? Suppose in this example, as you can see in this example, the predicted y value is here, yi, and this is the actual y value, that is y cap I, we can say. So I can take the difference between these two. So y predicted value minus y desired value. After that, I can square them up, and for all the points. So as we can see, multiple points are there. For all the points, we are going to compute the error, and after that, we do a sum over of all the errors. So that will be our sum of squared error. And our objective is to minimize the error for our model. And this is the cost which we need to minimize. And this is the cost which we need to minimize. That is why it is also known as cost function. So let me see some real life scenario. This is some unknown function which I need to predict. Maybe the temperature of tomorrow. So this is the earlier day's record. Like if these are the other parameters, then this would be the temperature for tomorrow. Or if these are the input parameters, then this will be the production yield of a particular company. So if these are the input X, the corresponding Y value is there. So these are the training data. And I am going to predict a model. So suppose this blue solid curve, this basically depicting this blue solid curve depicting our ML trend function. That means it is trying to predict the relationship between the input features and the output value. So in that case, if I feed some test data, this is the test data. So this is a unknown data to the model. So obviously, according to my model, the y value should lie in here. But in reality, this dotted black line, this was the actual relationship between the input variable x and the output variable y. So this should be the actual y value. Whereas my model is giving this as the output y value. So the difference between these two are the error of the model. Similarly, if, I just talked about the linear regression model. Similarly, another machine learning technique is called artificial neural network, where multiple neurons are there. Like you can see, these are the neurons, and this is this they are basically stored in a layered fashion. So you can consider this is the input layer or the layer 1, and you can consider this is the layer 2 or maybe output layer. So they are connected by a set of wires or links which is associated with the weights. So input feature x1 is connected with the next layer hidden node or output node with some weight w1. Another feature x2 is associated with the next layer node by the weight w2. This we use to set a bias node, which is again associated with the next layer node by some weight value w0. So as you can see, this is similar to the biological nervous system. So here, this is the dendron, which is connected with the axon. So basically, this is the dendrite. They basically receive the information. After that, they pass the information through action to the next neuron. So you can consider this layer is the this neuron, and this node can be the dendrite of the next neuron. So information is passing from this neuron or this layer of nodes to the next successive layer. And obviously, based on the strength or connection between the previous neuron's actions with the next neuron's dendron, these weights are assigned. So if these weights are strong, the input will influence the next neuron more promptly. If these weights are very less, it is not going to affect the next hidden node. And after that, this hidden node basically computing the weighted sum of all inputs. So x0 into w0 plus x1 into w1, x2 into w2, and we are summing over all of them. So from this, you can understand. Suppose I make this w1 as 0. Suppose I make this W1 as 0. In that case, this X1 input will not have any influence on the output value. But instead of making W1 0, if I make the W1 too high compared to W0 and W2, in that case, the X1 input will have most impact on the next layer neuron or node compared to X0 and X2. So this weight value basically influence how much impact a particular input feature will have on the successive layers of hidden nodes. If these weight are less, this input feature will have less impact on the next layer node. If the weight values are high, then the input feature is going to have too much impact on the next layer node. So this is basic working principle of artificial neural network. And based on their organization, there can be various types of artificial neural network. Like most common is the multilayer perceptron or feed-forward neural network or deep neural network. The deep neural network, the difference is that instead of one hidden layer, it having more than one hidden layer. Similarly, it is a clustering technique, self-organizing map. This is a feedback recurrent neural network. It is a kind of Hopfield network. So based on how we are going to connect these neurons one with other, we are going to get different types of artificial neural networks. So that was the basic discussion. So am I clearly audible to everyone?
Yes, you are clear and audible.
Okay, thank you. So I am now going into detail. I'm going to show a few demonstrations that how it can be solved in real life scenario. So we okay. I believe that we have learned what linear regression is. Linear regression is not a linear relationship. A linear relationship between an input variable and an output variable. And we all know the linear equation. So this is a linear equation. So x1, x2, x3, xn, these all are the input features. And for with the help of these input features, I am going to get the output value, which is fx or which is y. So we need to, the only job we need to do, we need to this W1, W2, W3, which are the coefficient of this input. We need to evaluate our model such that we are going to get the best combination of these coefficients W1, W2, Wn such that it properly depicting the relationship between the input features x1, x2, xn with the output variable y. So that is why I stated that x are the independent input variables and whereas y is the dependent output variables. Its value depends on the independent variable x1, x2 till xn. So if I go back to my previous example, I consider two input features. One is PLL and other one was HG. And this C is, you can see any straight line equation is also a linear equation where there is the intercept, no? Y is equal to mx plus c. So c is a constant term because weight alone cannot be deciding what could be the possible relation. They are in case of linear, obviously it should not always go through the origin. No? So that is why there should be some intercept value. So that is why C is there. And in case of neural network, this W are expressed as weight, whereas C is expressed as bias. Well, let us solely focus on linear regression. So it depicted linear relationship between the input features and the output variable. And for the purpose of evaluating the model, we need to know the mean absolute error. Mean absolute error is what is the error generated by the model and what is the actual, what is the output generated by the model and what is the desired output. That means what is the actual output of the model. If we take their absolute difference and compute, it is called mean absolute error. Obviously, one more thing you should have considered here, that obviously suppose our model is training with n number of samples. So I should take a, instead of this sum over, this should be sum over for all the n samples. So I should write down sum over I equals to 1 to n, and after that I should take the mod difference between the actual value of the model and the predicted value by the model. So these are the mean absolute error. Similarly, there is another metric is there to evaluate the performance, which is called mean square error, where instead of taking the absolute difference between the actual and the predicted value, we basically between the predicted and desired value, we take the square of the value. So suppose the predicted value is 4 and the desired value is 5. So the reference 4 minus 5 is minus 1, square of it is 1. So this is how I need to keep on computing the difference for all the training sample, what is the error amount. After that, I can take sum over for all the n input samples. And after that, obviously, as it is mean, I need to divide it by divided it by n, and I'm going to get the mean squared error. Root mean squared error is just root over the mean squared error. So because absolute error is depicting the real magnitude of error, whereas mean square error is not depicting the actual magnitude of error. It is basically increasing the magnitude of error. And that is why it is instead of using mean square error, you can go with the root mean square error. It is taking the second norm of L2 norm of the error, but it is not increasing the magnitude of error because it is applying square root after squaring. So it is normalizing the thing. And the third metric is called the root means R square metric. R square metric is another model which is used to fit the effectiveness of the model. Okay, let me explain the R square because it may not be known to everyone how R square is evaluated. So basically, suppose I need to evaluate a model performance. So I can take three examples. Suppose input is these are the desired value. Huh? Suppose this is the desired value. This is the predicted value. This is the error generated by the model. So suppose for the first input sample, the input desired value is 3. The model generated value is 2. For the second sample, suppose the desired value is 6. Suppose the model predicted a value which is 4. For the third model, suppose the model value is 9 and the predicted value by the linear regression model is 7. So in case of first model, the error is 1. In case of second model, the error is 2. In case of third model, the error is 2. Keep in mind that I have considering a mean absolute error in here. So obviously, if I want to consider the mean squared error, so if I want to consider the mean squared error, in that case, it will be 1, 4 because I am taking square of the difference, and this will also be 4. So in general, one second. So in general, R square is depicted 1 minus sum of squared regression error divided by sum of square total error. Now what is this? This is actually 1 minus, suppose y is my original value and the mean value. So for these three sample, what is their mean? Mean is 6. Mean is 6. So in this example, suppose I am using y bar to represent the mean. And for all the sample, I need to compute it. So take a sum over for all the sample, and it's preferred to take the square of it. So take square of it. And whereas in case of this is called the sum of square of total error. Why it is called sum of square of total error? That means I need to evaluate if these are the desired values. If they are the desired values, then how these values are deviating from their mean value. So how these values are deviating from the mean values. This is called sum of squared total error. Whereas sum of squared of regression error, it is different. It is the original value of y, that is y desired value, minus y predicted value. So this y, I can use a hat to say this is a predicted value. And again, I can take a square of it. So in ideal case, this value, in ideal case, this should be close to 0. In ideal case, this should be 0. So in ideal case, the r square should have a value equal to 1. So if your model give a r square value 1, then you can say your model is best. And in worst case, this is going to give us a value 1. If this module give us a value 1 or more than 1, if in worst case this module give us a value 1 or more than 1, in that case r square value will be 0 or less than 0. That means your model is too poor. So this is how r square is used to evaluate the performance of the model. Now, why R square is needed to evaluate the performance of the model? So, in general, suppose these are the desired output of a model. Suppose these are the desired output of the model. So, anybody without the knowledge of machine learning, I can take the average of the previous day's data and I can say, I can get the mean. I have all the previous day's data. I can just collect the previous day's data and divided it by the number of data or number of sample, and I will get the mean. And I can say, as this was the previous day's data, so next day data will be this. So mean can be easily computed. And if I say the mean value as the next day's value, that is the most easiest task to do. And below you can see this is the minimum. This is basically what? This is actually mean value. I am checking the difference from the mean. So obviously any model should produce less error compared to the error of the mean. And that is why the denominator should be a high value and the numerator should have a less value. And due to that philosophy, the r square value should always be close to 1. And in worst case, in extremely worst case, this model may generate more error compared to the mean value. In that case, the r square may even have a negative value. That means your model is performing worst. So this is how philosophically R square evaluate the performance of a model. Okay, now we have discussed too much about how ML model works. Now let me quickly jump into the code. Just let me know whether my screen is visible or not. Is my screen visible?
Yes, it is visible.
Yes, sir. It is visible.
Oh, okay, thank you. So in this example,
Yes.
I'm going to demonstrate. In this example, I'm going to demonstrate how to predict anything. So in this example, I'm going to predict the crop yield, but obviously it is not limited to crop yield. You can use the code. I can in fact share the code with the participant, and anytime they can run the code and evaluate the model. Give me a moment.
Yes, sir.
Okay, due to any reason, it is taking a little bit time. I will share the code. Okay, so I have shared this code with multiple people. So you also can work with the code. I think I need to close some tab. Give me a minute, huh? Due to 1 minute. Okay, I think in that browser I was facing some problem. Let me open a new browser, huh? So okay, I hope this screen is visible. So uh, as you can see, I have used a GitHub to store the data. So let me show the data. So in this model, what I am going to do, I am going to use a pandas library, and from the pandas library, so this is my data. I hope it is clear. So these two are input values for crop, and this is the yield or output value. And these are all the data sets. So first two are the input feature, and the third one is out. Now I am going to use linear regression to predict it. So first of all, let me run this code. So it is going to import the pandas library. After that, so it will go to my GitHub account and will collect the data. So and I suggest everyone to, if you are using GitHub, then you do not you should not access the data which is in tabulated form. You need to go to the raw data and collect the raw data from GitHub. Huh? Else it will not work in Poland. So as you can see, we have collected the data. So data.head, this Python code is going to show us the first 5 rows of my data. So first 5 rows are these 1, 2, 3, 4, 5. So I want to see whether I have properly collected the data or not. And due to that reason, I am just printing it in the screen. After that, you can see my next job is to split the data into training data, test data, feature, and label. So if I go back to the previous example, then I have put the data in a data variable, and this data variable is a pandas type of variable. The data variable data type is pandas data frame. So that is why it looked like this. So these are the input column, this is the output column, and each row depicting a particular sample or example. Now, I want to separate the input feature from the output, because for the training data, I am going to feed the input feature, going to predict the output value. after that going to compare the predicted output value with the desired output value. And for the test data, we will feed only the input feature and approximate or forecast the output value. So based on that feature columns, I have created a variable feature columns that will basically store two variable TLL and SD. After that data was my data frame name, which contain total data. So this is actually data variable, which is a data frame variable, which contain the input feature as well as output label or output variable. So from there, I am going to collect only the input feature columns. From data, I am only going to consider input feature columns. And after that, I am going to again print the first 5 value of the input features. Similarly, from the data frame, I am going to segregate the output variable. Output variable is yield. Output variable is yield. I am going to segregate the output variable into a variable y. Let me run it. So as you can see, I have divided my data into two parts, input variable and the output variable. So input variable X, these are the input values, and Y variable contain the output, desired output value. Now, if I need to implement linear regression, how I can proceed? sklearn dot linear model import linear regression. So here sklearn is a scikit-learn, science-kit-learn. It is provided by the Python. So this library contain another package, linear model, and that linear model contain a library for linear regression. If you wish to implement linear regression, you do not need to write all the code. You can simply import this linear regression class from linear model package, and it will perform the linear regression on the desired set of parameter values. And I am going to import another from scikit-learn, science-kit-learn, sklearn. I am going to import another package, model selection. From model selection package, I am going to import train test split. So this is another class that basically helps us to divide the data into training data and test data. So suppose I do not want to split the data by writing my own code. I want to use Python library that will randomly divide the data into training set and test set. In that case, I can use this function, class train test split. Let me run my code. So in this example, what I have done, I have used this function train test split. I have X is the input feature, Y is the output variable, test size equal to 0.15. That means 15% of the data I wish to use to test the model, and rest of the data is going to be used for training the model. So if I am going to test the model on 15% of the data, I am going to train the model on rest of the 85% of the data. So if I use 0.2, in that case, 20% of the data will be used for testing, rest 80% will be used for training. Random state. This is a random state that says what should be the algorithm, what should be the seed value of the randomly generation of the training set and the test set. So suppose, obviously we always, suppose I want to compare multiple algorithms. So multiple algorithms need to be trained and test on the same set of training data and same set of test data. So random state ensure that though it is going to randomly separate the data in a training set and a test set, to make sure the separation will be same in each and every case, the random state seed value is assigned. If the random state is 1, then it is going to split the data in a particular way. If random state is different, it's going to split the data in a different way. So, and linear regression is a class. So, if I want to access the function of the linear regression class, I need to use I need to create an object of the linear regression class. So in this case, linreg, linreg, I am giving an object named linreg, which will be an object of the linear regression class. You can give any name you wish. For better understanding, I have given this kind of name. So now by creating the object of linreg, I am going to call the fit function of the class linear regression. So in linear regression class, there is a function called fit. That function is used to train a linear regression model. So in this model, I am going to pass the input features, and I am also going to tell the model what is the expected output value. And this is why it is called supervised learning, because not only I am feeding the training data, I am also providing the output values to guide or supervise the learning method. So feed is used for training, and after that I am feeding the input feature, output values. So our object linreg has now learned by using the training data, training output values. Now I am going to use sklearn metric. Sklearn metric uh, contain all the metric used to evaluate a model. Metric I have discussed earlier, like mean absolute error, mean squared error, R square error, root mean squared error. These are the metric used to evaluate any regression model. So here I have imported this metric so that I can use these functions. Mean absolute error, mean squared error, root mean squared error, R square error. I do not need to manually write down the code to evaluate, rather than I can simply call the corresponding metric function, and it is going to give me the corresponding error value. That is the purpose of importing this library. After that, import numpy as np. So numpy is used in Python for performing any matrix computation, because we all know matrix computation. It is very difficult, and if a vector is more than two-dimensional, suppose n-dimensional where n is more than 2, so in that case, it will be very difficult for us to manually compute them. So that is why Python provides a NumPy library that helps us to compute any vector computation task, like matrix computation or tensor computation, like those kind of tasks. Okay, we are not going into the detail of that. So after that, let me show you how to predict. So that linear regression class also contain a function called predict. That the job of this predict function is to predict the output of a model. So suppose I am going to feed the test data. So X test is the test data which has not seen by the linear regression model earlier. And I want to predict if these test features are provided into the model, what could be the possible output of the model. So I am predicting the output of the model. After that, I already know the output of the test features. So the test output is already with me. So, and y predict is the predicted value by the linear regression model. If I run it, then it is going to show me, and I have used a zip function here. Zip is another function in a Python library. This function basically zip or attach to variables. So as you can see, y predict is a particular column vector, and y test is another vector which contain the desired output values. So zip function basically club them in a column wise, it concatenate them or club them. And after that, mv may be the predicted value and ab may be the desired value. And you can see that these are my predicted values, Whereas this is my predicted value, this is my test value, that means that real value or desired value, and this is the error generated by the model. So I have used a round function because in general, after decimal, it can keep on going, maybe for 12 positions. So that is why I have used the round function. And after that, I took the absolute difference between the predicted and the desired value. That is why F function. And I have round till 2 decimal position. So that is why you can see the error, it is showing up to 2 decimal position because round function I have used, and it is rounding off till 2 decimal position, and absolute because I want to have the absolute difference, not the actual difference. So this is the performance of our linear regression model. So suppose I want to compute the, like I told earlier, mean absolute error, mean squared error, root mean squared error. So root mean square means what? Square root of mean squared error. So if I perform square root on mean squared error, I will get the root mean squared error and R square score. So all these values, from all these values, we can see our model is not good. So linear regression model may not perform well if the data are complex. Like earlier example, I have shown you. Linear regression model is also always try to draw a linear curve. Like in 2D, it will try to draw a straight line. In 3D, it will try to draw a plane. In high dimensional, it will try to draw a hyperplane. But straight line or a plane may not be the ideal representative of the curve. So better to have a curve which has non-linearity, that I am going to discuss next. So this is how you can perform. Below I have also shown an example that you can perform, like in the slide I can perform. Suppose in the previous example I have split the data 20% for testing, 80% for the training. But suppose you do not want to do that. Rather, you want to perform cross validation, like explained earlier. So you can use cross validation and you can use 5-fold. If you use 10, it will divide the total data set into 10-fold. If I use 5, it is going to divide the total data set into 5-fold. So I have used 5-fold, and after that I have evaluated the R square value of the model, and from there also we compute and predicted the performance of the model. So this is how you can do the things. This is another data set for which I have evaluated the model, but where I have used the same train test. So leave that. Somehow it is not working. I will positively share these code links, which will help to further inspect the code and test how to improve the performance. So I would quickly jump, as we have seen that linear regression is a good model, but it cannot perform great when the data relationship between the input variable and the output variable are not linear. It cannot perform well. So let me quickly jump into polynomial regression. So the linear relation, we was assuming the relationship between input output variable are linear, like this. There is no degree, or degree is always one. So let me jump into polynomial regression. So a model that assumes a polynomial relationship between the input variable x and output variable y. You can see, suppose we are assuming that input feature having only one value, that is x1. So input feature is a scalar single value x1, and the corresponding value of fx we can assume it is y. And b0 is the intercept we can consider, and w1 is the coefficient associated with the feature x1. It is a polynomial of degree 1. Now we can consider one input feature with degrees of polynomial 2. So in that case, function can be represented as w0, w1 plus x1 plus w2 plus x1 square. Similarly, I can use polynomial of degree 2 with two input features. Here, input features are two, x1 and x2. So obviously the whole equation will look like this. W0, which is intercept, after the w1 x1, w2 x1 whole square, Then because it polynomial degree 2, so I will go till degree 2. So it is the degree 0. I can consider x1 degree 0, x1 degree 1, x1 degree 2. After that, for the x2 as well, the x2 degree 0, x2 degree 1, and x2 degree 2. And finally, we need to do their cross product. So x1 into x2. So this is the whole polynomial equation where degrees of the polynomial is 2 and input feature is also 2. Well, in reality, suppose you are having only one input feature and degrees of the polynomial are n. In that case, the equation obviously will look like this: w0 x1 to the power 0, w1 x1 to the power 1, w2 x to the power 2 till wn x to the power x1 to the power n. And obviously, if I want to consider polynomial of degree n with two input feature, then it is going to consider for x1 all the possible values of degrees. Similarly, for x2, it is going to consider all the polynomial degrees for the variable x2 and all the cross product of x1 and x2. So polynomial regression, we can see it quite complex, computationally more complex than linear regression, but it can tackle the nonlinear relationship between the input variable and the output variable. So in this example, for the simplicity, suppose we know two input feature is there, TLL and SD. Two input feature is there. And suppose I want to, for simplicity, I want to assume the polynomial of degree 2. In that case, it will be W1 plus W1 TLL, the input feature 1, plus W2 SD, the second input feature, then W3 first input feature square, TLL square, W4 plus second input feature square, SD square, plus W5, the cross of these two input feature, that is TLL into SD. So this will be the polynomial equation. Now let me quickly jump into the code of the polynomial equation and see whether it is able to enhance the performance or not. So first part is same. As you can see in the first part, we have taken the matplotlib.py plot that I am going to explain later. I have used to this I have used to visualize the data representation. After that, pandas I have explained, it is pandas data frame. It basically store the data in a tabular fashion. As you can see below, these are the row, these are the column, and these are the table column names. So TLL, SD, these are the input features, and dependent output variable is yield. And I have taken the data, the raw data from the GitHub. This data. Okay, how to go back? I'm facing the difficulty here. I I think it can be moved. Okay. Uh, so in this example, let me go down. After that, I have used the same process, like dividing the data into the feature and the output values. I have printed the values. As you can see that I have splitted the data into inputs and outputs. After that, this is a new. This is a new part I would like to focus on. So earlier from scikit-learn, sklearn, I have earlier phase I have used only two libraries. Like linear model, from linear model I have imported linear regression, and from model selection I have imported train test split. But here I am going to import these two libraries for polynomial regression. So from sklearn.preprocessing, I am going to import polynomial features that it is going to consider the high degree values like x1 square, x2 square, x1 into x2. So these polynomial features it is going to compute, and sklearn.pipeline import make pipelines. It is going to make pipeline of those nonlinear features. And in this example, suppose I would like to use the degree 3 because I feel the data is quite complex. So I want to, so if you use degree 1, it is similar to linear regression. Degree 3, obviously, it is a non-linear equation. So it is a polynomial equation. So this is the again same step. X is the input feature, Y is the corresponding output, and test I want to use 20% of the data to test. Rest of the 80% will be used for training. So I have I need to run it again because I changed the test 10 sample sizes. After that, I am going to use the function. So okay, this thing I need to tell. So I am going to call make pipeline. Make pipeline is a class in which I am going to pass all the high dimensional or high degrees of polynomial features, as well as I am going to pass one object of linear regression model. And overall object, I am going to name it polynomial regression. So polyreg. Polyreg is the object of the class make pipeline, which will be used for polynomial regression. And in this class, there is a function called fit function. This function is used for training the model. So in the fit function, I'm going to provide the input features and the output values. And I have already trained the model by clicking on the play button. Now I am going to do what? I am going to predict. So in make pipeline class, there is a function called predict that is going to predict the output on the test input features. See how it is performed. And similarly, I have used a zip function. And as you can see, this error is quite less compared to linear regression. Let me go back to the slide of the linear. You can see the error was quite high in case of linear regression model because it was failing to approximate the nonlinear relationship between the input feature and the output. Very. But here, in case of polynomial regression, it is depicting their relationship quite well due to high degrees of the polynomial. And similarly, you can compute the other metric like mean absolute error, mean square error, root mean square error, R square value. And these values are also R square value is 0.95. It is too high, too good. Whereas earlier the R square value is too bad. 0.39 is very bad. And uh, 0.95 is too good because the value, if it is close to 1, it is good. If it is close to 0, it is bad. And if it is more than, if it is negative, then your model is actually underfitting, not performing at all. Similarly, you can perform cross-validation where I have used a cross-val score function. It is dividing the data into 5-fold and scoring, that means evaluating the model based on R square. And after that, these are the output is given by the model. This is another, okay. So this is our output on the test data. So this is how polynomial regression also works. I will provide the code for the polynomial regression as well, but currently I'm facing some problem with it. If I slowly would like to, okay, this slide I can skip. I would like to talk about one more thing, like suppose till now I have talked about only regression problem. Let me quickly talk about a classification. See, uh, in this example, as we can see, KNN. KN is the K nearest neighbor classifier. It can be used for regression as well as it can be used for classification. Now, let me demonstrate how it can be used for classification. And this is another kind of machine learning algorithm. So, suppose this red triangle, these are the input features, and these are their associated output values, which are 1, 8, 9, like that. And this blue circle, this is some unknown new input sample for which I would like to approximate its output. So I can use k nearest neighbor to approximate its output value based on its neighbor. So if I consider k as 3, that means I am assuming it is having 3 neighbors. So if I assume it is having 3 neighbors, then it will the value will be evaluated by using 3 neighbors. Now suppose I assuming 1 neighbor. If I assume 1 neighbor, then based on its nearest neighbor, I am going to approximate its value. So its neighbor value is 6. So I will evaluate the new node, the blue circle node also having the yield value 6. If I use 2 neighbors, then the value will be 6 plus 2, 7. The new node value, if I take the average of 6 and 8, 6 plus 8 by 2, this node I will going to assign a value 7. If I consider 3 nodes, then I am going to consider 6 plus 8 plus 1. 6 plus 8 plus 1 is 15 by 3, which will give us 3. So in that case, I will assign value 5 to this unknown new input node. So this is how the nearest neighbor algorithm can be used for regression. Well, this KNN can also be used for classification. Suppose there are two classes. Like as you can see in this example, this person is sick. This is a group of person who are sick, and this is a group of person who are healthy. Now, suppose I feed a new sample. So this red oval class, this is a new person. Assume it is a new person. And I want to assume what class this input belongs, whether this person is sick or this person is healthy. How I can do that? I can use this nearest neighbor and neighborhood size 1. If I consider neighborhood size 1, then obviously the nearest neighbor is unhealthy or sick. So I will assign class as sick. Well, if I take 3 neighbors, then majority voting I need to do. Majority of the members belongs to healthy. So I will say the new class member is healthy. So this is how it works. Obviously, in case of classification, you should take k value as odd value, because if you take k value as even value, in case of majority, both the neighborhood may be split equally into two classes, and in that case you will not able to make the decision. So that is why for classification always use k as a odd value, as a majority breaker. Okay, so basically, what is the working principle of k-means? It basically measures the distance. Suppose for this class, it measures the distance who is the closest neighbor. So this may be the first closest neighbor, this may be the second closest neighbor, this may be the third closest neighbor. So for a new sample, it measures the distance from all its neighboring samples. So I need to have some distance metric to measure the distance of a new test sample with all its neighboring train samples. So majorly the distance metric we use is the Euclidean distance metric. I hope Euclidean distance metric is known to everyone. This is the Euclidean distance metric for if it is a n-dimensional data, so we take the distance between xi and yi. So xi may be the sample 1, and yi in n-dimensional space, yi be the another sample in n-dimensional space. We take their square distance, and after that add them up and finally take the square root. So this is how we measure the distance between 2 points in n-dimensional space. If it is 2-dimensional, then n will be equal to 2. So see the computation. Suppose 2 data is there in a 3D space. Suppose 2 data is there in a 3D space. So in that case, this is how we are going to compute. So in x-axis, this is the difference. In y-axis, this is the difference. In z-axis, this is the difference. And after that, we take the square root. And we get the Euclidean distance between 2 points in a 3D space. Okay, this may not be required. Now let me show how the clustering can be performed with the example of another, with the help of another example. Suppose, let me see that code should be there. K nearest neighbor. So this is the code for K. Okay, so run it. So KNN implementation of KNN is again simple. So in that case, as it is a classification problem, so I do not need to get the output value. Rather, I need to know in which class it belongs. So for that, I am going to use this class. So this is the class. So here ID is the feature you can ignore. Actually, it is numbering that how many samples are there. So basically, as you can see, it is 1, 2, 3, 4, 5, 6. So how many sample is there? Total 150 number of sample is there. So ID you can ignore. ID is not the feature. ID is basically the serial number. And actually feature are 4: sepal length, sepal width, all in centimeter, petal length, petal width. These are the input features, and species are the class they belong. So iris is a type of flower, and there are 3 type of iris flower are there: iris setosa flower, iris versicolor flower, and the third type of iris flower is called iris virginica flower. So in this example, I have taken 150 iris flower sample. 50 iris flower belongs to iris setosa category. 50 sample belongs to iris virginica category, and 50 samples belongs to iris versicolor category. Like previous example, I have separated the feature from their class level. So features are going to store only the features, and I have discarding this, actually discarding the first column. Why? Because the first column is serial number. So I need to delete this before computation. So that is why I have collected the all data using a data frame by using the GitHub URL. After that, I have collected all the features. Features are the sepal length, sepal width, petal width, and species. Later, I am going to separate these species features because this is features. This is not feature. This is class length. After that, I have printed the first 5 rows. This is how they look. After that, see, here I am basically separating the features with their class level. I know that first 4 column are the feature values, and the 5th column is actually their class level. So I have used Python array to store the first 4 rows as the feature matrix or feature variable, and the last column, first 4 column as the input features, and the last column as the output level. And this is how they look. After that, I'm going to introduce many functions. Like from sklearn.model, there is a package is there which is called grid search cd. Now you don't know when you are going to use k-nearest neighbor algorithm updating any classification task. You don't know what is the ideal value of k. You can go with k value 1, you can go with k value 2, you can go with k value 3, and you need to know what is the best k value for that particular data set. So that is why grid search is a grid like search. So I am going to use a n number of values of k, and for each values of k, I am going to see what is the least amount of error I am getting. So if I assume k as 1 and I get too much error, and if I use k as 3 and get to minimum error, so obviously k3 is a better choice than k1. So due to that reason, grid search CV is used. It basically use different values of, it will be used to get different values of k and their corresponding error. And the k value for which I am going to get the minimum error, that k value I am going to use on the test data. So this grid search is used to evaluate the error on the training data. And the k for which I am getting the minimum error, that k I am going to use on the test. Stratified k-fold cross-validation is a k-fold cross-validation means if k is 5, it is 5-fold. If k is 10, 10-fold. So stratified cross-validation makes sure that when I am dividing the data into multiple classes, multiple folds, I make sure that all the folds contain equal number of class representatives. And sklearn.neighbors, module, this module contains the class k neighbors classifier. This k neighbors classifier, the code is already written for k nearest neighbor classifier. We just need to create an object of this classifier and send the input parameters, and we'll get the value. Obviously, we need to pass the value of k, the number of neighbor, as well. Scalar metric that I have not used, so I can delete it. An scalar metric, obviously, in case of regression, the metric was mean square error, mean absolute error, root mean square error, R square. Whereas in case of classification, the metric are like classification accuracy. That means what is the percentage of correctly identifying the thing. Suppose I feed 10 samples to the model, and among the 10 samples, the model is correctly identifying 8 samples, and 2 samples it is not correctly identified. So what is the accuracy? Accuracy is 80%. So accuracy means the percentage of correctness. Recall is another metric that I am not going into the detail. Recall means after feeding feeding multiple more examples or samples, how many of them it is correctly identified. Like I have feed 15 dog images to the model. Now model is correctly identifying 13 dog images, and 2 dog images it is failed to correctly classify. So that is called recall. That means how much example it is correctly able to recall. Similarly, F1 score, it is basically a balancing between precision and recall. ROC curve, AOC curve, those things are going to ignore. So, like in a previous linear regression and polynomial regression, here also I am going to use a k-nearest neighbor classifier. I am going to create an object and name the object as model. Now this model, I am going to use a range of values of k. So k values in this example, I am going to consider from k value 1 to k value 30. As range function takes the value from the initial value till the n minus 1. Now, so if it is 31, it can take maximum 30 values. So k range is k value is from 1 to 30. This number of input. After that, I am going to this parameter grid. I am going to use a dictionary. This is a particular package available in Python. And neighbors, I am sending the neighbor value can be 1, neighbor value can be 2, neighbor value can be maximum 30. So I am going to create a parameter grid where basically this is the parameter grid is what? Parameter grid is a dictionary where it will have a key value pair. Let me explain with better words. So it will have a kind of this value like n neighbor. So one after that n neighbors will have a value 2 like that. So it is kind of dictionary. So here in node will have a value. In node will have a value 30. So this is going to create a dictionary like that. After that, I am going to use stratified tenfold cross validation. So iris cloud is 150. If I divided it by 10, then I am going to have 10 number of folds, and each fold going to have 15 number of samples. So 15 samples will use to test the model, and rest 135, 150 minus 15. 135 samples will be used to train the model, because I have used tenfold stratified cross validation. After that, let me plot for which k I am getting a best value. So as you can see, grid search CV, this is a class I have called earlier. And in this class, this model is what? Model is actually KNN model. I should have named it KNN model. So this is a KNN model. Model is the KNN model. And after that, this is fit function. This grid search CV contain a fit function. It is used to train the model with training data. Now I need to evaluate the model. So I need to evaluate the model, and I need to check actually for which k value I am getting the best data. So this, for each k value I am going to get a value. For K1 I got 96. For K2 I got 95. For K3 I got 96.6. Well, it is very difficult to inspect this big list. So let me do a help towards us. So I plotted it. For K1, the value is 96. For K2, this was the value. For K5, so this is how we can understand, maybe close to 14, maybe close to 14, this may be 18, 21, 14, 18, 21. For these values, I am getting the maximum accuracy, maximum performance. So it is wise to choose less number of neighbors. If you use more neighbors for computation, then it will be obviously costly. So it is always wise to choose if it is equal, then choose the least value of k. So here I can use, if it is 40, then I am going to use number of neighbor as 40 to test my model on the test data. So this is the from scalar metric. I have imported accuracy score, precision, recall, all confusion matrix, classification report. Let me run my model. So in this example, oh, right. So I have considered 14 neighbors. So k nearest neighbor classifier, this is the class name. Number of neighbor I'm going to consider 14. So KNN is the model name or object name of the KNN classifier. This KNN.fit, it is going to train the model, train the model. Okay. So this is the prediction result, and so this is how it is performing. So this is the confusion matrix, and the accuracy is quite high, so 98%. So that is it for me today. If anyone having any question, please ask. Anybody having any question, please ask. Sorry, I'm unable to hear. Is there any issue?
Hello.
Hello. Yeah, you're clearly audible.
Good afternoon, sir.
Good afternoon.
Sir, actually, If I put this data directly on the system, then can I get the result?
Yeah,
This
you
code and
supposed to.
this code. Mm-hmm.
Uh, I was facing some problem. I am
Yes, sir.
supposed to provide the data. I will obviously, the coordinator, Professor Arnav Ghosh is there. I will
Okay.
positively share the code and GitHub link to him.
And the
Hope
pandas,
and he will.
sir, the data from the pandas will have to also we have to retrieve the data from there.
Yeah, basically the data is Pandas is a library which actually retrieve my data from
Oh,
GitHub. So I will provide the GitHub link where the data is. I will provide the
okay,
code
sir. Thank you,
where the code is. You can
sir.
reproduce it.
Yes, sir.
Hello, sir.
Hello.
Is the session completed, sir?
Yes. If there's no more question, we can.
Any questions from the participant? Then we can going to conclude the session.
Okay, sir. Thank you, sir, for sharing your valuable knowledge on the topic application of machine learning in renewable energy.
Hello, sir.
Sir,
Yes. Hello.
hello. Sir, am I audible, sir?
Yes, you are audible.
Sir, sir, please, sir, explain the concept of hyperparameter tuning, sir, for validation, sir.
Like in the previous example in KNN classifier, you have seen that for different key values we can get different result. So
Yes.
we have used grid search CV, and grid search CV helps us. Suppose you have the training data. So
Yes.
what you can do, suppose you have 100 data set, total 100 data set you are having. So you can use 70% of the data to train the model. After
Yes, sir.
training the model, suppose let me explain with KNN because I have taught KNN. So suppose you train your model with 70% of the data with some k value 1. After that, you need to evaluate the model on validation data that has not been used during training. So use
Yes.
20% of the data and see how much error you are getting. Similarly, you are going to use k-value 2 and train the model for 70% of the data, evaluate the model on validation data on 20% validation set, and check the error amount. So by using this means the k-value for which we are getting the minimum validation error, that k-value
Yes.
we are going to use to test our model. So for different ML method, different parameters are there, but that can be evaluated by using validation data set.
Yes, sir. Okay, sir. Thank you. Thank you, sir.
Thank you.
I
Thank you,
hope
sir.
no more queries from the participants end. So thank you, Professor Prasenjit, for giving your valuable time and very good discussions about ML applications for the renewable system as well as EV. Okay, as well as for your hands-on session. I hope participants will get a lot of benefits from your lecture. Okay, so thank you. So now we are going to conclude our current session, and our next session will be started in very soon, I think after the lunch.
Hello, sir.
Hello.
Thank you.
Sir, is it okay from your side so that we can take some photo if you on your camera?
Okay, no problem, sir. No problem.
Okay. I'm requesting every participant, so please on the camera so that we can take some group photo. So thank you everyone. Now you can switch off your camera. It is okay. So thank you everyone for joining us. Here we will wind up our session. I am requesting everyone to proceed for lunch. After the lunch, we will be gathering here only for listening to the keynote speech of Mr. Dibbaraj Krishna on the topic gallium nitride application for EV and solar power converter. So we will start our next session nearly at 2:15 p.m. Thank you everyone. I am sharing here in the chat box feedback form. So please fill it as soon as possible. Thank you.